Good day, everyone. Today we'll be taking sort of like a twist from what we've been doing so far. We've been treating analysis. Today we'll be treating physics, cinématique du point matériel. Another cinématique du point matériel, we'll be treating étude du mouvement en coordonnées polaires. In more videos to come, we'll be seeing more topics concerning cinematic as well as other modules, analysis, algebra, and so on. So always try to stay tuned. So now we can start. So what is there to know about étude du mouvement en coordonnées polaires? There's some basic things that we're supposed to take into consideration. One is the rayon polaire, which we denote as RT. You'll be seeing it in some of your exercises like in your TDs. And we have it as OM, vector, function of time. And then long polaire, theta t. It is found in OX of OM, like this. Now we say that it varies with time, and then we note this R as the rayon. The rayon, we say it's the radius in English, and then the angle theta, which is the angle theta. And what do I mean by this definition? Let's say I have this is not, I'm not using scale, and I have theta, I have M, I have R. For example, like I said, RT, this is O, this is OM. Okay, now RT, if we're dealing this in function of time, let's say R is with OM, and then if we're dealing it in function of time, R is with OM theta, OM in function of T, I'm sorry. Now for long theta, we see that it's always in the direction of OX. It's always in the direction of OX, proper OM. So one thing we should know is that it can vary with time. When we take more examples, we'll be able to understand how exactly we can distinguish this. But what you should put at the back of your mind is when coordonate polaire is mentioned, think R and think theta. The other thing we should also remember is the vector unitaire, the unit vector. In coordinate polaire, we have two unit vectors. We have UR and we have U theta. UR is always in the direction and sense of OM. Let's say it's always in the direction and sense of OM. So this is OM. UR is always in the direction of OM. And U theta, before I draw it out, let me explain it. U theta is obtained by rotating UR. So when you rotate UR, you obtain, from here, if you rotate UR à partir de EM, remember, à partir de EM, that's from here. When you rotate your UR, okay, there you find your U theta, vector unitaire. This is no, it's something close to this. So yes, so I repeat, we have two vector unitaires. We have UR and U theta, and UR is in the direction of OM. U theta is gotten by rotation of u theta. And when you do that rotation of u theta, what do you obtain? So I said this is not really, you obtain p pseudo, it's 90 degrees. So it's, when using trigonometry, we say it's in p pseudo pi over 2. That's like 90 degrees. So when you rotate this, you have it in 90 degrees. So the other thing we should also know is their derivative. And to derive ur and u theta, the derivative of ur, so it's d ur over dt, over dt. The derivative of this will be d theta over dt u, okay, and the derivative of du theta over dt will be d theta over dt ur. You should take note of this maybe in your jotter or something, because it's very, very important. We are going to be using it. I'm not going to give you like the complete code. I'm just going to give you the important details that you can use to answer any type of question in coordinate polaire. So this is their derivative. The ur over dt is equal to d theta over dt u theta vector in it there, and du theta over dt is equal to minus d theta over dt ur vector. So that we take that into consideration as well. Then another thing we should consider is in our coordinate Cartesian, that's x and y axis. In our x and y axis, I think we have okay, remember I'm not drawing it to scale, I'm just remember that this, okay, m theta toujours r par rapport à OM. So this, when we have our coordinate Cartesian like this, what's the relation between the coordinate polaire and the coordinate? What's the relationship between the coordinate polaire and the coordinate Cartesian? The coordinate polaire, r and theta. Remember, we're dealing with r and theta. That's our coordinate polaire. Do not forget that, please. So our coordinate polaire r and theta au point m, du point m, is given by this relation. R is equal to x is equal to r cosinus theta, and y is equal to r sinus theta. So par rapport à x, the relationship between the coordinate Cartesian x and y and the coordinate polaire r and theta is that in the x axis we have it as r cosinus theta, and the y axis as r sinus theta. Of course, there's a way we do to get this, but like I said, I'm only bringing out the important points that will be used in your TDs. So now another point will be another thing we should also know is vector position, vector vitesse, and vector acceleration. So for the vector position, the vector position, we define it using r theta and ur. Remember here we have our r par rapport à ur, okay, with om, of course, om, à l'origine E, jusqu'à M, so OM. So to find the vector position, the definition of it, we use the R in function of time. If we're using it in function of time, we have R in function of time and UR, the vector unit vector. So the definition of vector position, a position vector position. Anyway, the definition of that is OM vector égale à R UR. So this is our definition of the vector position. OM est égal à R UR, vecteur unitaire. Now for the vector vitesse, that is, vitesse is velocity, vector is vector. So for the vector vitesse, we actually get the vector vitesse from position. Like if you're moving, remember in Ttable that if you're moving from position to velocity, we differentiate. From velocity to acceleration, we differentiate. Then if you are coming back from acceleration to velocity, from velocity to position, we integrate. So here we are moving from position to velocity, so we derive. So we have V is equal to d OM over dt. And what was our OM after from our other relation? We have OM in function of time is RT U R T. Now what's more important here? The important thing is after deriving, you get, like after doing the whole this thing, we'll have dr dt ur plus r d theta over dt u theta. This is like this is theta, this is theta, this. So we'll have this at the end, and then we can call this VR and we can call this V theta. So what are we going to be having? We're going to be having VR UR and V theta U theta. If you really want to see how it is being derived, I'm quite sure a professor will do that in course, but the whole idea is like, yeah, Monterey needs to get the definition, and when you derive it, this is what you're going to get. So remember, like I said before, that I'm trying to bring out the important point of coordonate polaire that you'll be using these definitions to prove in your TDs, to answer questions in your TDs. That's what's going to be more important for me based on what I've experienced as well. So VRUR plus V theta U theta. So finally, after finding this and this, what are the composants de la vitesse, composant of the velocity? We can now finally say it is VR is equal to dr over dt, which is this relation here, and then V theta is equal to R d theta all over dt, which is this one that we have here. So you should write this down in your jotter. Now VR, which is equal to dr over dt, you might say, you will see in your TDs where they'll ask you to find the composant radial and the composant traversiel de la vitesse. Yes. Now what is the composant radial and the composant traversial? tout simplement, the composant radial is your VR. And your composant transversal is your V theta. So all you do is you'll be given R, and all you have to do to find the composant radial, you derive R to get velocity, and that will be your composant radial. For composant transversal, you'll be given theta, an expression for theta, function of time, and then you'll be asked to, this is R, the R that was given here, you put it here, you replace it with this R, and then derive that theta that you'll be given at the beginning. That will be your composant transversal. Yes, that's how. That's how it is. That's how it is. So another thing that we have to take into consideration is, like I said, is a vector vitesse. Now, vector vitesse. For the vector vitesse, we've treated that. Okay, sorry. The vector acceleration. For the vector acceleration, we obtain it like we did for position to velocity. We obtained it by deriving. I will repeat the statement I made before. If you're going from position to velocity, you derive. From velocity to acceleration, you derive. Now, if you're coming back from acceleration to velocity, from velocity to position, you integrate. So now we've gone from position to velocity, and now we're going from velocity to acceleration. We are going to derive. So to get the expression of vector acceleration, we get it by deriving from the vector vitesse. So we get it by deriving this expression. So I'm going to, like I did here, I'm going to repeat the same process. So acceleration, which is, we denote this in vector. Don't mind my vector sign, but you get the point. So it's dv over dt, like when passing, this is, we're deriving it from velocity. And what was our v? What was our v? This v, it was this, right? So this is what we're going to have. We're going to have d dt, okay, of dr over dt ur plus r d theta over dt u theta. So this is what you're going to have. Then after you've broken down this expression, you've broken down the expression, what are we going to have at the end? Don't be scared, but this is what we're going to have at the end. Important thing is getting the definition and the main expression. So don't be scared about this last step. So I'm jumping to the last step after doing all the whole, because after doing the whole thing, this is what we're going to get. We're going to have d square r over over dt square minus r d theta over dt square, everything here ur. Maybe you can write this in your jotter, like I always say, and then 2 dr over d theta over dt plus r d square theta over dt square, and then u theta. Okay, now I feel like I should actually break down this expression for you, but I'll do that in my next video, or like in videos to come. I will try and break down the expression so that you get the whole idea like very well. It's actually interesting. Yes, it is interesting to prove it, to just break down the expression and then come to this conclusion. It's interesting. So I will try and then same I'll do it for velocity as well in my other videos, but for now just take this important point. Now we have yes, this is going to be, I can call this just like we did here, I call this VR, I call this V theta. Now I can call this entire expression here AR, that is this AR, and I can call this entire expression here A theta. Always remember we're working with R and theta. So I can call this is my AR UR, and this is my A theta U theta.